10, the two components are W1, W2 there. So what is the Q discipline and output?
Output is the Q discipline at the output will be first in, first out.
That's true. Now we are, when any packet is suffering WM at about delay, after we are calculating W2, and this W2 is coming batch size I we are considering. Out of batch size we are
within batch you can be placed anywhere.
Anyway, but we are selecting randomly.
Yeah, is with equal probability. Your tagged packet with equal probability can be anywhere in the batch size of I. But anything with the earlier batches has to always go first.
So
there is a first in first out among batches. Within a batch it's a random placement.
And when we are doing the tagging
is just a concept. Tagging is a concept actually, because actual tagging is not happening in the
That's
batch.
true, because we are calculating the probability tag packet coming batch size of I. So we are assuming that the total size is I. One already we selected, so n minus 1 we are selecting C minus I minus 1.
It's not clear.
So we are calculating the probability tag packet coming in batch size of I. Probability
At the output, whether the batch size of I is coming or not, what is the probability of that?
Out of n we are taking
the maximum batch size is n, minimum is 1. What is the chance that in a given slot at an output port a batch of I will come?
I will come, but one packet is already tagged in this particular packet.
Out of this I, one is my packet.
My packet, so we have this.
And it has the batch size has to be actually more greater than or equal to k plus 1 for a W2 is equal to k.
That's true, but for we are giving n minus 1, C I minus 1.
One is my already tagged packet which is coming from one of the port. Now from remaining n minus 1, I minus 1 should also come. Then only batch of I will be made. Tagged packet anyway is part of it actually. That's the reason why it was done. So ultimately, yesterday what we got was probability that your tagged packet will be there and it will suffer a delay of k. This is what we had estimated, and this was nothing but summation of ai by t. I goes from k plus 1 to n. Okay, that's what we actually have got. And ultimately from here I can find out what is going to be the z transform of this, which is a probability generating function PGF. So I have to just do summation for k going from 0 to n, because that's the maximum which is possible, the probability. Your batch, the W2 delay cannot be more than n, because your batch size cannot be more than n. So the maximum is what you will get is actually n minus 1 delay. It's not n but n minus 1. So you have to do z raised power k, and then of course whatever is this probability that W2 is equal to k has to be put here, which in turn will give you so this actually can be solved to find out what is going to be your probability generating function W2Z actually. So this is W2Z. That's what we are interested in. So you can actually now solve for it. So this one is pretty straightforward once I give the technique. So 1 over p I can always take out. And then of course ai we already know that is equal to ai, and I can solve. So when k is equal to 0, for that there will be a series multiplied by z raised power 0. For k is equal to 1 there will be a series. Number of terms will start reducing as my k increases. So I have to actually basically write all these terms and I will just reorganize them. But there are many ways of doing it, I will just do it this way. Okay, well, that's the way I have learned it. So for k is equal to 0, what is the series I am going to write in the first row? So this will be nothing but NC1 this is for the k I is equal to 1, and then of course you will have a series. I am not going to write all the terms, but so that corresponds to when when k is equal to 0. Okay, when k will be equal to 1, in that case all terms will be multiplied by z raised to power 1. I will actually have, because k is 1, so I has to be 2 minimum. And so on. You will have z raised to power n minus 1. Okay. NCN. I can write similarly for z square. I think by this time you must be understanding. You can write any term by just close observation actually. Okay, I made it has to be z square.
Z?
It has to be z because z has been multiplied. I am sorry for that. And so on till the last term which is going to be there. Z is for n. Last row will always actually have only one term. So you can now combine them. So you take only this term, you take the term corresponding to NC2, corresponding to NCN, and you will end up in getting nothing but the first one will have only one, there is no term. So there is only one term which is 1. Summation of that, because in every series, first time series only with one term, second time series is 1 and z, third time series 1 z, z square, 1 z, z square, z4. The last series will contain 1 z, z square till z is power n. This series you can always put GP and then put the things, and this will give you the complete thing. So I will just write the final thing. So you will have 1 over t will be out, z minus 1 by z minus 1
So last term will be j to the power n minus 1.
Z square NC n minus 1 or n plus 1 ratio.
J to n minus 1.
right. That's right. It has to be n minus 1. And so on. and of course you can write on the last term. Okay. So the last term will be now NC n P by n. Which is 0. So that's where the term actually closes. So I can actually take 1 over P z minus 1 out. Okay. This now can be written as summation of from I is equal to 1 to n z over I ai. Okay. Minus this minus 1 is there. This very well can be now written as 1 over P. Now this term can be written as 1 minus a0. So I can write as this. I can combine this whole term. A0 can be taken inside and I can make this, and this is nothing but a probability generating function of ai, az. So expression will be az minus 1 divided by p z minus 1, that's w2z. Okay. So I can now combine these two things together. In fact, there would have been another simpler way of doing it. You multiply by z and then subtract the two terms whenever you want to find out that kind of series. That is also another simpler way. That z minus 1 would have come out, upper one would have been simply z minus 1. So either way is actually fine. So now w is equal to w1 plus w2, which actually implies w of z is w1 of z. This is a standard result again from string theory for probability generating functions. So whatever is the addition of the variables will become nothing but multiplication PGF domain. So this actually means you will have Q of z one minus A of z, P 1 minus, I have actually taken 1 minus z, so upper one is also 1 minus az. So that will be the final PGF. You take the derivative of this and make z is equal to 1, that will give you the mean value of w bar. So you take that thing, so this value which you will get is nothing but q bar plus second movement around 0 and first movement around 0. First movement around 0 is mean. Okay. And A bar is P. Because n into P by n will be P actually. The average value will be A bar. And of course, A square bar also you can estimate, this should be P plus. These are again all standard stuff. Then P map. And from here you will get W bar equal to whatever was W1 was n minus 1 by n, I think P square 2 P minus 1, 1 minus P8. Yeah. So that's for W, this Q bar, plus the second term now you can put from here, This will turn out to be p by 2 n minus 1 by n. You solve for this particular one. A square you take from here, this a bar you take from here, put it here, solve, you should get this. And this in turn will give you this, which is nothing but this is average delay for MD1Q. Only factor which is multiplying factor is n minus 1 by n. So it technically all output queued system will actually work like MD1Qs. And the beauty of it is if you want to actually plot with P with the maximum throughput. So when n goes to 1, this term goes away. We have P by 2, 1 minus P. Okay. So if you solve for it, this is nothing like a saturation. The delay also goes to infinity. So earlier case, the Q length, they all will go asymptotically when P is equal to 1. So same is with the delay also. Okay, it's so that you can actually operate at any value of P, it does not matter. Only at P is equal to 1 you go to infinity, which anyway is unstable for any kind of Markovian arrival process. P is equal to 1, you will always be unstable. We have seen that for MM1, infinity Q at some point of time earlier. Okay. So output Q is actually the best option if you can achieve that. But you need not be able to implement that all the time. So what we can do is now move over to the input queuing system for comparison purpose. Input queuing system I will never be able to achieve very close throughput. So when P actually increases, throughput is increasing, it will try to reach to basically as far as possible, only the queue will build up, but my throughput performance will always become very close to 1. So 1 packet per slot I will be able to push at the output port. Only my buffer length requirement will be high because of the randomness, because of the contention. And if you somehow can ensure that there is no contention, throughput will be 1. But input queuing, because there is a head of the line blocking, we can actually again do that modeling and find out what's the approximate value. So it's about 53 something percent or 0.53 something. That's the maximum throughput which can be achieved if I am going to have head of the line blocking in the input queue.
In the previous analysis, we are able to only conclude thinking either Q will behave like MD1 with some multiplied factor.
Yeah, it's n minus 1 by n. That's the only difference which is coming because of the batch arrivals. Batch arrivals technically act like a Markovian process. So let's come to the input queue system. Now this is going to have many outputs and there are n inputs. Again, I am not worried about that n minus 1 only will be package distribution. No, I am not bothered about that now. We have the buffers at the input. At any point of time, I am now looking at for one particular output I. So whatever is true for this ith output is also true for any other output. Okay, it's an equivalent system. There is no bias. So I can just take one output and analyze for that. Now what will happen is the packets will keep on coming at the head. Once the packet will come, so for this ith thing, there can be, only look at the head, how many packets are there. So at the head, for trying to, the packets which are trying to reach to destination I, let those packets be numbered as BMI after nth time slot. One thing you should be sure that summation of BMI over all i's, all possible output combinations, Okay. So 1 to n, this should be equal to how much? This only says that for I, how many packets were queued up in the front of the queue? For I is equal to 2, how many are queued up? Total number of queued up packet which is there in the head of the queues has to be equal to n only. This cannot be less or more. In worst case, it is n. If it's in every slot, if the packets are coming, fully loaded condition. Okay. So this will be equal to n for saturated condition. When there is always a packet available at the input in every time slot. In fact, a similar kind of equation which we had done earlier is also hold true. Whatever was the, after the earlier time slot, whatever was the number which was queued up, one of them will be picked up and will be sent to the outgoing port, remaining will remain there at the head. Only thing now, the balancing conditions will be different. There will be new packets which can arrive in the nth time slot, which I will again write as AMI for the at output port. Now remember, these will be not out of n. Earlier case it was out of n actually. Out of n, I packets are coming in the batches. Now it is whatever are the ports for which the packet has been pushed out to the outgoing port in the m minus first slot, only on those lines new packets will be coming in. And from those only I will get some packets which will be destined for I. So I will not use n here, I will use something else when I will make an estimation. And one packet which will be going out. So this relation is very similar. So in fact a very similar result can be used here also. Okay. Except now that I will not be using n, I will be using something else here. The probability factor which was there will actually get changed. That's the only thing. So the probability that your AM I will be k. I will not use n. Earlier I was using n here. These are free ports on which the packets will arrive in the queue through free head of the line queues. Front of the queue, which actually has become free. In the next slot, packet only will come on those. This FM minus 1 is that number. Ci with equal probability. I am looking at a saturated condition. So P is equal to 1. So I am trying to find out what is the upper bound on the throughput performance. Under saturated condition, whatever you achieve, you cannot achieve better than that. Okay. Unless we do some manipulation, we will do that actually. So it's 1 by, this has to be there, 1 minus 1 over n. Okay. Now, what is this FM minus 1? So this is by definition. Whatever is the blocked queues, I sum up all of them for each outgoing port. This value I have taken in worst case will be equal to n. But ideally speaking, this should be always less than or equal to. The difference between them is what is FM minus 1. Okay. So n minus, the difference is this. That should be FM minus 1. Then of course, FM minus 1 should be equal to, that's where the new packets will come. Should also be equal to this. Arrivals, new arrivals. So these two conditions should always be satisfied. And I can actually make an estimate of, I can call something called F bar, which is mean number of free input queues after every time slot. This is statistical average of this under a steady state condition. Then let that be f bar. So you can actually observe that f bar by n, that much fraction of packets will be going as a throughput. That's the maximum which you can achieve. What is happening is in the switch, in this case some packets remain, some move. Some packet remains, some moves in every time slot. On an average, the fraction of packets which are moving out divided by total lines, that should be the fractional utilization of each outgoing link. That's the load, that's the number of packets going out, but no packet is being lost here, remember. It's an infinite buffer. So this has to be equal to rho naught. I am interested in finding out what is rho naught actually. Now, there is an approximation here. It's a very simple judgment. When n goes to infinity, this AI under steady state condition EMI will tend to become Poisson statistics. So new arrivals which are coming in will be nothing, they will be Poisson with parameter rho naught. Okay. Because that's a utilization, average utilization coming. So it should be Poisson statistics with rho naught actually. So I should call it the steady number of packets for output I which is AI. I am not writing M because it is a steady state number. This is Poisson with parameter rho naught.
Rho naught is output utilization. Output line utilization.
Yes.
What
You are putting packet all the time, but you have to maintain a steady state. So output utilization has to be equal to input utilization. Okay, if input utilization is good, because there is a maximum which you can achieve under saturated condition, you cannot have input utilization higher than this. If you are going to have it, your Q will blow up. It will not be a stable Q. So stability condition does not come at rho naught is equal to 1, which was happening in the earlier case in output queuing system, when P was utilization of every link. When it is going to 1, then only you are going to instability. Here you will actually achieve instability even before that. See, that's a bad thing about input queues. So you will blow up to infinity only even before P actually goes equal to 1. Okay. So P has to be maintained at lesser than 1 for input queued switch to operate. So there is a chances you may actually lead to instability, because P is equal to 1, most likely you usually never operate with that P is equal to 1, fully saturated condition. So what I am saying is, under fully saturated condition, your Q is going to blow up, but there is a maximum utilization. So if you keep input utilization equal to output utilization, your Q will be almost kind of stable. Just it will actually blow up at that point. But anything which is below rho naught, it is going to remain stable.
That means output buffering is better.
This always, obviously. Common sense tells it has to be actually better. So once this is rho naught, you look at this expression and this expression. This is very similar to what we did in output queuing. I had a very similar expression. This was a Poisson statistics for n is equal to infinity and for binomial for finite number of n. And we could directly estimate what was the statistics of the output size. It was MD1Q thing. So I can use the same result here. But n is going to infinity, so n minus 1 by n is 1 actually. So what ultimately you will get is the Q length. I don't have to put V I bar. This value will be how much? Now it is rho naught. I am not going to put P, it's rho naught. That's actually equal to P. P is also utilization. But I am using rho naught here. That's what it will be. And of course, now I can use this expression Under steady state condition, m actually can be removed. This value will be nothing but
1 has to be also divided by n in this case.
n by n. N by n becomes 1. Okay. So b I know already from here, so this 1 by n can be taken out. Okay. So now solve for this, the upper one. So this is nothing but rho naught under steady state conditions. 1 minus, and you will have 1 over n. So for each of these component summation, I am taking bar actually on top of it. Both, I am taking expectation on both sides. So this will be nothing but n number of times you are going to add bi bar, which is nothing but rho naught something. So this should be, because I am actually having n terms, all same values is multiplied by n. This can be cancelled with this. Solve for this rho naught. So you should get 1 minus rho naught is equal to rho naught square plus rho naught square minus 4 rho naught. There also has to be a 2. Fine. So this rho naught square I can make it equal to 0. This is the equation which you will get. Solve for it.
Two minus root two.
Yeah. So you will get actually these two solutions for rho naught. Rho naught can never be greater than 1 obviously. So 2 plus root 2 cannot be the solution. So only possible solution is 2 minus root 2. So that's the maximum throughput performance which you can have out of a input queued switch. It cannot be better than this. And this number I think turns out to be 0.586, 58.6%. So this actually means at the input side, number of packets which are coming on every incoming port on an average per unit slot has to be less than 0.586 for stability. So because what is happening is as P changes, your throughput performance rho naught actually will change with this and it will saturate roughly about 0.58. So throughput is saturating but my input is high. So somewhere, so if the input is higher and output is low, what will happen? Something has to be stored. Flow is not balanced. And where it will be stored? In the input queues. So queues will blow up ultimately. So which is not good actually. So you have to always operate below 0.586. Now question is, can I do better than this? Is it possible? I think it is possible to do better than this. So what we do is, this actually means we are going to operate if there is an input queued switch in two possible ways, so that I can improve my throughput to about 80% actually. Instead of limiting myself to 0.586, 0.88 something I can should be able to achieve. I cannot still go to 1. So what we have to do is very simple rule. So far my P is less than 0.586, I will keep on operating here. Suppose if what I do is, instead of this, whatever packets I can transmit, I transmit. If I cannot transmit, I don't keep them. I don't keep head of the line blocking, I just simply drop those packets. let the new packets come in. Okay, so now, and that will improve the throughput performance. Remember, there are now two phenomena which are happening here. One is the packets which are arriving at the input. When you are actually working with lower P, lower arrival rate, then less number of packets are coming. So what happens is, even if you keep head of the line blocking operational, does not matter, because packets most likely won't come and you should be able to transmit. So you achieve a higher throughput performance. After certain threshold, if you don't drop the head of the line packets, that blocking itself now will cause you the loss, because sufficient packets are anyway arriving, so that you can achieve higher throughput performance. So from there this actually idea came. So if you start dropping the packets, how you will estimate the throughput? Every time there is a fresh lot coming in the front of the queue. So what is going to be performance? What is going to be the throughput performance of the ith output? So far, even if I get, what's the probability that I will get one or more than one packet destined for I out of this n? That will be the throughput performance. So that's the probability that you will have a packet in the outgoing slot. If you have one or more than one being destined for this. If it is more than one, then only one will be going. If it is less than one, or it is 0, then nothing will be going. So 1 and 2, 3, 4, 5, for all of them only one packet will be going. So you just estimate that probability that I will be greater than or equal to 1. That is nothing but your throughput performance rho naught. And this probability is 1 minus NC0 P by N this is nothing but 1 minus so that will be your rho naught or the throughput performance. And when n goes to infinity, then what will happen? This rho naught will become 1 minus e raised to power minus p. Now how many packets are being lost per line? Your incoming rate is p. P number of packets are coming per line per unit slot, while your outgoing is rho naught. So how many packets are being lost? P minus rho naught packets are lost per line per packet. So this is a per line, the whatever is being lost. Per line per slot, yeah. Per line per slot, these many packets are lost. So P are arriving, rho naught is going out, P minus rho naught are going to be lost. And if you know how many packets are coming, you divide by that. So this should be your probability that a packet, a tagged packet is going to be lost. So this will become that probability. So this is the probability that a tagged packet will be lost. And then of course, now your rho naught is 1 minus e raised to power minus p. For a given p, this is what is the value in this case. When this is going to be greater than or equal to whatever I have solved for fully saturated condition, 2 minus root 2. Find out the values of p for which this is going to happen. So till 0.586, if my p is till that point, it is fine. Okay. After that, I want to actually have higher throughput. So what is the value of p? So from here you should be able to get a value of p which is equal to so this is the crossover point after which you should start dropping the packets. Okay.
So ये minus minus 2 and plus 2.
Hmm?
No, correct. 1 plus 1.
Which one?
Inside the log.
And you solve for it. Actually, it will. Okay, let me solve for this. This is pretty simple. So if you write these two equations, this will turn out to be root 2 minus 1. Root 2 you on that put on that side.
Greater than equal to equal minus 1.
Okay, this 2 minus 1 is 1. 1 minus root 2 minus e raised to power minus p. So root 2 minus 1. I will change the sign. Okay, that's the way it will come. And then of course this is nothing but you multiply by root 2 plus 1, divide by root 2 plus 1. Okay. This will turn out to be 1 actually. 2 minus 1 is 1. And then you take the log, so p has to be greater than or equal to natural log of root 2 plus 1. Okay. So the moment you cross over this particular value, so you have to estimate what is this value. You will find that your this is, remember, is this throughput is dependent on p. At certain probability, this will be better than the saturation throughput. At that particular point of p, you should switch over. And then when you put p is equal to 1 here, that's the maximum which you can achieve. You cannot achieve anything better than that. You put p is equal to 1, so 1 minus 1 over e, which is roughly I think 0.88. 0.882.
Basically, we are applying the hybrid approach.
No, what is this value which will come? I think this is 0.882 when you start dropping the packets. But you cannot actually operate. You have to start dropping the packets when it crosses 0.86, 586. And that's the maximum which you can achieve. And anyway, when you are dropping your packets, your buffer will never be filled up. Everything which is coming afresh all the time. So you have to start dropping the packet on the tail side of it also. No, when you are dropping, there is only one buffer required per input. Okay. So this actually means you can actually operate with input queued switch, but you have to have an operating regime. So whenever your input arrival rate is less than 0.586, it's fine. The moment create 0.586 is going to explode. It's better to switch over to dropping the packets, and it will keep on operating. And in this zone, you will find out you're dropping this thing actually will always give a better performance. Okay, for dropping the packet situation. So this is actually another. There are two thresholds because of this. So one is because of stability region, I have to switch over. So 0.586 whenever it is there. So till this point, I will be operating with ordinary strategy. Head of the line blocking will be happening. At this point, actually instability happens. So I have to switch over to dropping the situation, but I may not be still getting only getting 0.586 performance. It will not be better. It will only become better when I will cross over natural log of 1 plus root 2. Somebody has the calculator to find out the value. I think it's 0.88. That's what. It should not be 0.8. It should be the same value.
0.88.
0.88, no? Yeah. So this is 0.88 till this. After this point, you will start getting the benefit. So below this, you are operating below without saturation region. You are operating in saturation regime here, where you will only operate the throughput of 0.586, and after that you start dropping. So even if you had drop or does not drop does not matter, because even if you are dropping, your performance will be poorer than 0.586. So Q will remain unstable. That's the only problem in this zone. So what you do is at the input buffer, you limit your length of the queue. So if the queues get fully filled up, you start dropping the packet. That's the only way, because you don't have infinite buffer. you require infinite buffer for this operating regime. Okay. So usually buffers will always be finite. Once they fill up, you start dropping. You don't actually store any incoming new packet unless head of the line gets cleared. At this point, you start dropping from the head of the line, because then throughput performance will be better than 0.586. Because if you drop from head of the line here, you won't get a better performance. Your rho naught will be lower than 0.586. At least you are operating at 0.586, which is maximum possible. So at this point, it will start becoming better. So I think it should be something like this, the curve of the throughput, and then here it will become better, and to reach to 1 over, because that's what you get the maximum. You cannot get anything better than this. What is this value? 1 over 1 minus e?
0.38.
0.38. No, it should be higher.
0.63.
0.63. So how come this one value is? Oh, this is rho naught. That is p is equal to 1. Okay. So at 0.586, 0.63, whatever you will be reaching here, and you will saturate with that actually. So 0.586 to point whatever is 60, which is this value, that's where you will saturate with. Okay. You cannot get anything better than this, is not possible when p is equal to 1. So that's the maximum in the input.
Sir, utilization is arrival rate by departure rate or departure rate by arrival?
Utilization, no, it's not the ratio. It is, you look at the output line for how much fraction of the time the packet is there. So if it is slotted system, in every slot what's the probability a packet is there. So if you observe for 100 hours, so whatever is your utilization into 100 hours, for those many times you will see the packet, for remaining time you won't see the packet. Utilization, how much you are utilizing the link.
Generally in Q system we will be taking lambda by mu. Lambda is the arrival rate and mu is the departure rate.
No, that's a load, that's not utilization. That's a load. Lambda by mu is the load factor. That has nothing to do with utilization. You can compute utilization in those terms, that's fine. Usually that is known as load. Load is also technically equal to utilization under steady state conditions. That also gives you the fraction of the time for which a link will remain utilized. Link will be having some packet.
Here we are dropping the packets right in a queue in HOL.
So incoming utilization is higher than the outgoing utilization.
Is there any relation between the next packet which is coming in the same queue? And
All are independent. There is no correlation.
so
Markovian arrival process actually means every packet is coming independently. I am only assuming a parameter called probability p. In a slot, a packet is there or not there. Next slot, if a packet is there or not there, is independent.
And how these lost packets are recorded? How these lost packets?
We don't recover, they are gone. That's a responsibility of higher layer. This is what is technically known as congestion. See, your switch has the capacity, but there is a congestion building up because too many people are trying to go through the same line. And you have to be dropped because it cannot go through. Congestion cannot be cured in the network, in any switching node or any link. Only thing is that you can start reducing your traffic which is being pumped into. You go onto the road, for example, go to the city, try to drive. There is a congestion, what you have to do? Do you get a solution? No. Best is you can start improving utilization or some discipline. You can still improve the performance, but if it is still there is a congestion, you have to live with that. Or best is don't go. So have a radio broadcast telling everybody there is a congestion on this road, please don't drive through this. So incoming rate itself you are trying to reduce, and that will then keep the congestion within limit. And that also what we do in networks. In TCP algorithm, for example, there is a TCP Reno algorithm which technically does this. It guesses when the congestion builds up, it will start reducing its transmit window. So you pump less number of packets per unit. But everybody should do it. It should not that there are 4 honest guys who are doing it. This guy says, okay, now the channel is available, let me push through. So this kind of free riding can actually happen. This happens between UDP and TCP, for example. UDP does not have congestion control. Last semester I have taught this. So if you are transmitting, say, audio video transmissions typically on UDP, and you are doing a file transfer, network congestion happens, your file transfer will slow down actually because of congestion control algorithm. UDP, there is no congestion control. It will see a very good bandwidth, it will actually even pump more. You can actually conduct this experiment, try downloading a heavy file, few GB, and also try to play a video. Make sure it's a UDP transport, this one is TCP. And let the link be congested. And you will find your video actually will still perform better, not an issue. What will suffer is always the TCP traffic. Okay. This is an observation. We are still looking for better algorithms for doing UDP based congestion control.
So excuse me. In that figure, what is the abscissa corresponding to 5.586?
This one is T.
No, sir. On the y-axis, what is the
Y-axis is the utilization rule.
No, sir. The value corresponding to 0.586 on the y-axis.
This one.
Huh?
Roughly you will be increasing, and there will be some formulation based on that. It might vary this one.
Sir, what is that rho naught corresponding to?
Rho naught is output port utilization.
Corresponding to 0.586. The value, sir.
Maximum you can get is only 5.586 is this thing. Actually this will be lower. This is not 0.586. But you will saturate at 0.586, this much I know. This 586 might be happening somewhere here. Okay. So your saturation will actually start happening before it. It's not the knee point. It's somewhere here make the 0.586 happening. I have not done the exact calculation. But see, by intuition, important thing is by intuition and by understanding, I should be able to predict. I should be able to generate a hypothesis. So science is all about that. So gaining an insight based on that, predicting something. Okay? Okay.